This is our Chapter 11 Lesson 2 video, and we're looking at inference for relationships within distributions of categorical data. So in the last lesson we looked at whether a distribution of categorical data on a one-way table, so one variable measured different categories and counts in each, we looked at whether that matched up with what our expectation was, and oftentimes in terms of probability or in terms of the census. So now we're going to be looking at two-way tables and looking for associations, meaning values of one variable in the table affecting values of a second one. So keep in mind our guiding question here. What does it mean for two samples or categories to be independent? So what's the conceptual idea of that? And then what does it mean mathematically? What does it mean when there is an association between the two in terms of probability? And how can a chi-square test for homogeneity detect association and independence? It's a nice idea to look back at chapter 1 real quick and look at two-way tables. Most of that stuff's pretty straightforward, especially at this point for you guys. So a quick brush up on independence. To analyze data, we oftentimes compute percents or proportions, which we've been doing all year. There's two different ways of producing data from two-way tables that lead us to two different types of chi-square tests. Remember, association means values of or outcomes of one affect the likelihood of the value of another. That means the probability of one outcome changes if another one occurs. And in mathematical terms, the probability of A doesn't equal the probability of A given B. This means the event B happened already and the probability of A. That's what this means over here. This means B happening changes the probability of A. If these two were equal, they'd be considered independent. If they're not independent, this means that B occurring somehow changed the likelihood of A occurring. So independent random samples from different populations we're interested in and a random comparative experiment, then we can classify all of it according to a categorical variable of interest. So remember, categories meaning like color or race or gender, and then counts within each of those categories. Our null hypothesis is just the same as before, is that the distribution of this categorical variable is same for all populations or treatments. So we could be comparing two different populations. And if we can reject that, then we can prove that it's different. So maybe outcomes like gender or race or something else is affecting values of another variable. So this would be a chi-square test of homogeneity. And we use to compare proportions of successes for each of several populations. So we could look at two races or two genders. We could look at multiple races. So if we wanted to see about proportions for multiple populations that are based on the different ethnic background. If we have data from one single random sample from a population, then each observation is classified into two categorical variables. So before, what we were just talking about was the same variable but for two different populations. Now we're looking at one single random sample from a population but more than one variable being measured, more than one categorical variable, and then seeing if there's an association between those two categorical variables. Whereas before we were seeing if the population from which the sample was drawn affected the outcome. So this would be a chi-square test. So we have a single SRS. Then we're going to do a chi-square test of association or independence to see if values of one category are associated with values of another. Remember, association is not causation. Two things can both be effects of another lurking variable. However, it can tell us a lot about what to expect or give us clues as what to do next, what to investigate next that may be causing this association. The null hypothesis will be that the two categorical variables are independent, meaning one outcome of one doesn't affect the probability of another. If our values are far enough away from that, we can reject that and show that they're not independent. We're going to do the expected count, since it's a two-way table, will be the row total times the column total over the table total. We're going to look at this in class more about how to get that expected count and why that works. We're using the same formula for a chi-squared statistic where the sum is over all the cells in the two-way table, so every cell included. So we will state what test we're going to use, our null hypothesis that there's no difference in the distribution for several populations, our alternative that there is. We start by calculating chi-squared, and if all of our conditions are met. and then we go ahead and calculate it, find a p-value for it, see what percent of values are to the right are larger than it, and then conclude based on that p-value. Now remember, we're always measuring distance from expected counts, which is a positive thing, so we're always a one-sided test. We're looking at values greater than or equal to the chi-square statistic, so this area under here represents that. With small values being small likelihood that the null hypothesis is true, larger values being more consistent with the null hypothesis. Remember to always check your conditions, that the large sample size conditions are new when it's based on expected counts, which we never round off because they represent the long term over many repeated samples, the average, and that those need to be at least 5. You need to show that for all possible values. Random and independent are the same as we've had before. If we find a statistically significant result, a small enough p-value, we do a follow-up analysis and try to find what the biggest component of it, the chi-square statistic, was. So that's the main gist. We're going to get more into exactly how to use these two different tests in class as we can walk through a problem together. So here's your multiple choice. Based on percent of SHC seniors. Note that this is not legitimate. I made these numbers up to match our problem with no particular goal in mind, other than knowing that you guys are all thinking about college at this point. So, which of the conditions has been violated here? Go ahead and pause now, read over the summary for 11.2, look over practice problems there, as well as explanations, and then submit your free response answer below in your multiple choice.